Okay, so in the last section of the chapter, 14.9 to 14.11, we're talking about how the structure of a chemical affects how acidic it is or basic it is, its acid-base properties. And in 14.9, it talks specifically about bond strength and polarity of molecules and how that affects whether or not it's going to be a strong or a weak acid. So generally speaking, the more polar of a molecule you have, the stronger the acid is going to be. The reason why is because if it's more polar, then you've got, polar molecules have the positive end and the negative end. If it's a more polar molecule where that negative end is more negative because of its electronegativity value, that greater charge separation means that there's a greater probability of dissociation. And that's basically because if this negative end is so strong, has a strong electronegativity, then it's easier for it to win the tug of war for electrons, and so the hydrogen is just barely hanging on, and so it'll just kind of let go and dissociate into solution a lot easier for the more polar molecules. Molecules with strong bonds are generally weak acids because if there's a strong bond holding the hydrogen to X, whatever X is, if that bond in between there is very strong, then it's going to be not as easy for that to dissociate and break off, and so there won't be as much dissociation, and so it's a very weak acid because you don't have as many hydrogen ions dissociating in solution. Examples of this, hydrochloric acid, that's a very polar molecule and a very strong acid because it dissociates very easily. That hydrogen kind of falls off. It's a situation we have up here where it's very polar. And another example, any carbon-hydrogen bond is a nonpolar bond. It's also very strong. So they don't have any kind of acidic properties. There's no dissociation of hydrogen ions. Okay, there is an exception here. Hydrofluoric acid. We know that hydrofluoric acid is a weak acid just from memorizing our strong acids and knowing that that's not one of them. So it's a weak acid, but it's very polar. And right up here, we said that very polar molecules are usually stronger acids. So here's where hydrofluoric acid is an exception. Even though it's very polar, the bonds are very, very strong because of the size of these two atoms. Hydrogen and fluorine, both very small, and so they're very close together. So the bond that holds them together is very strong. And so the strong bond wins basically over the polarity of the molecule, and it's going to hold that hydrogen in, and so only a little bit of the hydrogen will dissociate in solution, and so it's a weak acid. Okay, whereas the other halogens are strong acids, hydrochloric acid, hydroiodic acid, hydrobromic acid, are still very polar, but their bonds are not strong enough to kind of win over that, so they are strong acids. Okay, now oxyacids. Okay, oxyacids are those that have hydrogen. That is the key part. And the number of hydrogens, so it'll be an oxygen bonded to a hydrogen, and then X just represents, it could be another chain of a molecule or just whatever it is over here. The number of oxygens affects how acidic the molecule is. You should know that the acid strength increases with the increasing number of oxygens. So the more oxygens you have, the more acidic something is, and the reason is because if you add oxygens, then the molecule becomes more polar. So let's take a look at this example, and this example is you don't have to redraw it. I'm going to give you guys a page number. It's in your book. It's on page 662. So if you don't want to write it down, but if you want to just make a note, on page 662 is where you can see this diagram. Here we've got different variations of molecules, all with different numbers of oxygens. And by the way, you normally on the AP test, you don't get a lot of questions on this, but you might get like one multiple choice question. It's a good multiple choice question, common multiple choice question, where it just basically says which one is more acidic. And so, yes, you can simply memorize that the more oxygens there are, the more acidic it is, and that's easy to do. But you should know why, and it has to do with increasing polarity. Oxygen is a very electronegative element, right? It's like the second most electronegative element compared to fluorine. So if I have the polarity over here, the negative end is going to be in that direction on the molecule. That would be the dipole moment, right? We draw those to represent dipole moments. This molecule, so there's one oxygen. Here's two oxygens. So basically I've got two oxygens. They're going to pull more with the electrons. So that's going to be more electronegative. The negative end is going to be more negative. If I have three oxygens, then my dipole moment is even bigger. That negative end is even greater. And then four oxygens over here is very polar. It's pulling on the electrons so much over to this end. This, of course, would be the negative end of the molecule, that the hydrogen is barely hanging on right there. And so it will easily dissociate, just break off of that molecule because it's just barely hanging on. These guys are winning the tug of war for electrons, basically. So the hydrogen will very easily dissociate.